Good afternoon.
Good afternoon. So I have just sent you an email of a von Neumann diagram with labels by letter. And what I'd like you to do is to open your email and then hit the reply button and then put A and give me the name of the part, the name of the component. And then put B and the name of the component, and C, the name of the component, and D, name of the component, E, F, G, H. I want you to notice that they're not in order in any particular fashion, right? So, but you need to be able to know these by heart. And the only way to do this is to practice it. So I want you to spend the next 3 minutes, open your email, just click reply, right? Not reply all, but reply, and then put A, and then type out the name of what the von Neumann part is for this, right? And everybody go. And by the time we end up calling time, I want you to click the send button, okay? Does everybody understand what we're doing?
Yes.
Yes, how many minutes?
3 minutes, starting right now. 3 minutes. So you have about 90 seconds left. And when I call time is up, if you're not completely finished, I want you to just hit send. And I'll need to see 8 messages in my inbox. I'll see the reply back from you. Please use reply and not reply all. Okay, time is up. If you could click send. What I need you to do is to, if you haven't clicked send at this point, I need you to click send. Okay. So once again, you want to be able to label from memory. So label A should have been memory, label B should have been CPU, label C should have been input, and so on and so on and so on. You need to be able to type in the same information that you see on this diagram in the empty using the template that I showed you. You need to be able to type out data or the word instructions or instruction, ALU, right? Register, control, memory, input, output. If you miss any of those, if you misspell them on the assessment, you're likely to lose credit. The only way to get good at this is to take a blank diagram like we just showed you. Whoops, a blank diagram we just showed you, and practice. So what can you expect on Friday? We're going to start promptly at 1 p.m. on Friday. We have a lot to cover. And we want to get started promptly at 1 p.m. But I'm going to email you this same diagram, ask you to do it again in 2 minutes. And I want to see how well you're doing. So on Friday, we're going to do it for credit. If you get it wrong on Friday, no credit. It is an assignment, what we call a quick shot or a lightning credit opportunity, I'll email this to you. I'll ask you to label, just put A dash, give me the name, B dash, give me the name, C dash, give me the name. You'll have 2 minutes to fill out as much as you can. If you get most of it, you'll get credit. If you get less than half, you won't. Does everybody understand what we're doing on Friday?
Yes.
I understand.
Okay. If you didn't get all of them correct, just like you see here on this screen, then you need to practice. I want you to get good at it. I don't want you to lose time during an assessment. These are basic things, but you have to know them well enough because, well, they're the foundation. It's like knowing your math tables. How long does it take you to do long division if you don't know your multiplication tables? Oh my goodness. Yeah, it just takes forever. You know what I'm saying. Any questions about what's expected?
No, I just have a clarification. So if we put CPU or control processing unit, it would still be the same thing, or you're just looking for CPU itself?
If you put either, it'll be fine. That's a great question. So let's say that instead of memory, you put RAM. If you put capital RAM instead of memory, that would be fine.
Okay,
Yes.
gotcha. Thank you.
Yes. If you put arithmetic logic unit, that would be fine. But it's probably quicker and easier to put ALU. Lowercase, uppercase doesn't matter. Title case doesn't matter. Capitalization doesn't matter. Spelling matters. You can put control or controller. Okay?
What about control unit?
You could put control unit, but you'd be better off putting controller or control. You'd be better off doing it just like I have it on the screen. So I will try to remember to include, so in the assessment, I have to type out all the different possibilities, including misspellings. So, so sometimes people put it in enter, they enter something and they don't get credit because they misspelled something. Or they put control space unit, and I didn't have control unit, but I will specifically try to remember control unit. Okay, it's a good question. All right, so what we want to do is continue our review of content from module 4, and we got about this far yesterday where we talked about data buses and how they all come together in two main portions of a motherboard or a system architecture board, right? It's a printed circuit board, very large printed circuit board. A lot of system architecture is laid out on a motherboard, a system board. And the two main bridges, North Bridge and South Bridge. Does anybody remember how we distinguish North Bridge and South Bridge?
Okay, North Bridge is where all the data are being processed.
Well, there is data processed on both bridges. So that would be a partial answer, but we want to distinguish between North Bridge and South Bridge.
North Bridge would be where all the high-speed connections will need to be.
Right. The CPU and memory and any other high performance components. The CPU and memory and any other high performance components would be connected on the North Bridge versus the South Bridge. South Bridge is primarily involved with input-output. Okay? Input-output. All right. Give me 1 second here. Just need to update this. Okay, so let's talk about the system types of system memory. Now, when we say memory, here is where we're going to have a problem. So we have non-volatile memory, which is in a hard disk, and we have volatile memory, which is in RAM. And the von Neumann diagram just has the word memory. When I'm talking about system memory, I'm talking about both hard disk and RAM memory. And I'm talking about registers on the CPU. So when we talk generically about system memory, we are talking about any memory register that is capable of storing a data, or instructions, right? So that could be in the register on the CPU, it could be in RAM, right? Or it could be in persistent memory, non-volatile memory on the disk, okay? And what I want you to be able to do is to compare and contrast the types of system memory, including the performance latencies. So one of the things that we have to consider about computer architecture is the idea that the farther away you get from the CPU, the slower things are. Remember that the South Bridge is slower than the North Bridge, that the CPU and memory, RAM memory, random access memory, volatile memory, is located on the North Bridge, and you could have a graphics processor, like an NVIDIA graphics card with a highly specialized graphics processing unit that can be used for very high rates of floating point calculations that are great for gaming graphics or for high performance computing. Well, what am I saying? You can take NVIDIA cards and you can throw them into, the slots, the expansion slots on the North Bridge. So off the North Bridge, you have these expansion slots, and you can have an NVIDIA graphics card, an NVIDIA graphics card, an NVIDIA graphics card. And basically, there is memory, dedicated memory, very high performance memory on the graphics card, on the NVIDIA graphics card, along with the GPU. So there's memory on the CPU, which is represented here just by a square box or a schematic. There's memory in terms of RAM. There's memory on graphics cards or other components, right? And then there's memory when you come out of the south bridge to the hard disk. There's persistent memory on the hard disk. And the latency refers to how long it takes for something to get to the CPU. Okay, so when we talk about latency, we're really talking about the amount of time something takes to get to the CPU. We have a table here in your study guide, and it talks about the memory register, the memory type, right? So this is system architecture, and this has to do with types of memory. And if it's SRAM, S means static RAM. And there are two types, actually three types of static RAM: level 1 or L1 SRAM, level 1 static RAM. Just remember the S stands for static, and it's sitting on the CPU. That's the register that we're talking about that sits in the CPU. Well, it's additional memory that's closer to the register in the CPU. So you have registers right in there, right? And you have this small amount of memory right next to the arithmetic logic unit. And the speed is about 20 nanoseconds, right? And when it comes to the volatility, in several clock cycles, it's gone. So what am I saying? In 1 or 2 clicks of the CPU clock, which for a gigahertz machine happens 1 billion times a second, the information has already changed, right? So this table will show you the relative use, right? What it's used for. This is used for CPU cache. So if there's memory cache right on the CPU chip, that's called static RAM, and it's either level 1 or level 2, right? So you have a smaller amount of RAM that's closest to the CPU, and then you have a larger amount of RAM that's a little further away from the ALU. It's still on the chip, all right? But it's toward the outside of the chip. When we say chip, technically what we're talking about is the package. So a CPU core is the guts of the arithmetic logic unit. And let's see here. Can everyone see this?
Yes.
Yes.
So generically people say, oh, there's the chip. No. No, that's what they refer to as the package, right? So when you mount it into a socket on the motherboard, the cores, the computational cores of the CPU, or dies, right? When you talk about the actual CPU itself and not the packaging around it, oftentimes that's referred to as a die. And if it's a multi-core processor, that means that there's more than one CPU on the package, right? So an Intel Core Duo has 2 dies or 2 cores. That means it has 2 CPUs bundled into the package. The package is what mounts into the socket on the motherboard. If you flip this over, you have something that looks like this. So you have all these pins on the bottom or connections on the bottom. And then on this side, you have the dies or the cores, okay? In any case, what I want you to understand is that there are memory registers that are built into the package. They're built into the actual core itself. That's the L1 cache. And then there's an L2 cache that's part of the package It's a little further out. It's not sitting on the core, but it's next to the core. And this stuff is super wicked fast memory. It's a form of static RAM, which is not to be confused with SDRAM. So whenever you see this, dynamic data rate, DDR, it's talking about dynamic RAM, that's system memory, okay? So SRAM is a very special, very expensive, very small, sits closest. It handles the most calculations, the information that's used the most and most often. I'm going to interject something here, and in our draft, I'm going to say something about the 80-20 rule. Let's see. So I'm going to get back to this in just a second. Everybody help me remember 80-20. 80-20. So what's the 80-20 rule? A long time ago, efficiency experts figured out that you use 20% of your resources 80% of the time. So if you have data and instructions, 20% of your data and instructions are used 80% of the time. There's another name for this, and actually there's several names for it, but I'm going to call this Zipf law, maybe. Okay, Zipf's law. It has to do with the distribution of resources and how frequently they're accessed. So it has to do with frequency of access, but 80-20 is the most common statement or common name. Oh, okay. So the Pareto principle. That's a very, so now you're going to find different names for this concept, but basically the whole idea is this efficiency ratio comes up over and over again. Now I say ratio. In computer science and in computer architecture, we say that 20% of your resources are used 80% of the time. In the context of Pareto's principle, they're talking about client and distribution and sales. So 80% of sales comes from 20% of clients. And so Pareto is an application of the 80-20 rule in the context of sales and customers. Okay, Zipf is another application of 80-20. Now, why do you care? Why should you care? 20% of your resources on a computer system are used 80% of the time. So if you can get those 20% of the resources closer to the CPU, you can increase the performance dramatically because it doesn't have to go as far. But the further away from the CPU you go, the more latency, or the longer the distance and the slower the access time. So what am I saying? 5 nanoseconds is extremely fast. Okay? The actual registers on the CPU themselves are very, very tiny. So you have memory registers built into the CPU, and they operate on a 5 nanosecond level. And then you have this SRAM, static RAM cache that's on the die, right? And that means that some of the 20% of the resources is stored in here, but only 64 kilobytes, right? So this is bits. That's very small. These are kilobytes. These are megabytes. So as you get further down the line, you tend to get larger in size. You tend to get slower in speed. You tend to get further from the processor. You tend to get less volatile, meaning if there's a power disruption, the chances are better that the data is going to last, okay? And I want you to understand where you find this on the system board. So in the processor, inside the die, next to the die, the SRAM, the L1 cache, a little further out, still in the package, closer to the memory, the RAM, okay? And then you have SDRAM, okay? Now, you need to understand, whoops, you need to understand the name of SDRAM and its different flavors. And there's a Wikipedia. There's all sorts of links in this study guide. The one you're about to get, there's lots of links. And I am not going to delay any further than today to get the draft out there so you can start studying. But no, I don't want this. Okay. So you do have different types of dynamic RAM. DRAM stands for dynamic RAM. And the S stands for synchronous. I suppose you have asynchronous RAM and all this kind of stuff. But the point is, the most common form of RAM, random access memory, volatile memory. This memory is SDRAM. The register in here is a memory register, and then right next to here would be something called the L1 cache, and then a little further out on the edge of the package would be L2 cache, closest to the memory, right? So the whole idea is to take advantage of this 80-20 rule, to put more and more memory a little further out, so that basically you take advantage of the 80-20 rule, you get the best efficiency out of a system. You have different dynamic data rates. So DDR is a criteria or an attribute of synchronous dynamic RAM, right? And basically, you can have DDR3, you can have DDR4, you can have DDR5. These are all data rates, and the higher performance, usually the higher the number, the higher the performance, the better the speed. But one thing I want you to understand is how this table is arranged. The further down the memory type you go, the further away from the CPU it is. The further down this table you go in this column, the larger the memory tends to be. The further down in this column you go, the slower it tends to be. Do not let this confuse you. This is not a faster speed. It looks like this is faster than this speed. This is the amount of time in nanoseconds. Let's make it simple. If I had some memory that took 5 seconds to access versus 100 seconds, which one do you think would be faster? The 5 or the 100?
The 5.
Exactly. Now, when you go from here, nanoseconds to microseconds, you go from billions to millions. So there's a huge drop. When you go to the EEPROM or EEPROM, right? It's made with NORs. It has to do with BIOS. That's it's non-volatile memory. And it's further from the CPU, but it's because of the way it's built, it's kind of like the only exception. If you run down this column, this particular row is probably the only exception to that whole trend. Where you run down, it tends to be further from the CPU, it tends to be larger in size, it tends to be slower in access, you know, that kind of thing. And it tends to be more non-volatile. So page file or swap memory. This is memory on the hard disk that's swapped out with RAM. And so this would be high microseconds. This would be low microseconds. So what am I saying about swap file memory? What is swap file memory? Let's Let's take a look at this again. So you have so much RAM on your system. And as you start loading applications in the operating system and you power on your system, more and more this gets taken up. And if you run 3, 4, 5, how many of you run more than one tab on your browser? See, I'm just teaching class here, and I have five tabs open. Who has more than 20 tabs open on their system right now?
Not, for me, not really. I've less than 20, more, 10.
Okay.
10 tabs probably.
Yeah, 10 tabs. So
I don't have any.
Like 15, like 15.
So let's say you have 15. That means you're taking 15 whole loads of your system RAM to represent all of the graphics, all the stuff in here, all the processes that are running for each tab. I'm oversimplifying, but let's say we have a smaller laptop and it doesn't have a lot of memory. Every one of those tabs could take up all of, a big chunk of memory. Well, every time you switch between the tabs, it has to go somewhere. So it switches out to the hard disk. You have big chunks of memory that it's like fake memory. It's near the front of the hard disk. It's called page memory or virtual memory. Here's another look at virtual memory. If I go into properties, oh, that's not where I want to go. Control panel. So if I go into control panel under system, well, now this is annoying. This is really annoying. Yeah, that's the screen I want, system properties. The newest version of Windows 10 changed up on us. All right, so right here, you'll notice there's a performance option under advanced. It shows the computer name. I can change the name or whatever. So if I pull up system properties, there's an advanced tab, there's a performance tab. It has to do with memory usage and virtual memory. Page file memory is memory that is used to switch out large chunks of RAM. And so, but it's on the front of a disk, the quickest part of access for a hard disk. So it's used as fake memory, fake RAM, when people are multitasking a lot of applications, a lot of tabs in their browsers. And it is a type of system memory. And it works like RAM, but it's actually disk. That's a specialty topic that we spend a great deal more time investigating in the operating systems course. But the thing I want to impress on you is that something called virtual memory or page file memory is further away from the CPU. Now, how many of you have heard of solid state hard drives?
I have.
Yeah, I heard of it.
I have.
Yeah.
Yeah, so solid state hard drives are much faster than traditional hard drives. So if you happen to have a solid state hard drive, it's gonna produce many gigabytes of persistent memory, right? But it's further from the CPU. You have to get to it across the South Bridge bus, the South Bridge, right? On an I/O bus. It's 80 microseconds. And then if you have a regular disk, a regular hard disk, that's 500 microseconds. So there's a huge performance increase. But you have still more storage by doing this, right? So that's real helpful. And then USB, you have an external hard disk. If you have an external hard drive, you go from microseconds to milliseconds. So now you're not even on the system. You're connected to a USB port across a USB port or a cable, right? And that's milliseconds. That's thousands of seconds, millions of seconds, billions of seconds, right? Billionths. So we're talking about the fastest to the slowest. You need to know the order of this, right? So other than registers on the CPU, what's the next fastest? SRAM, level 1 cache, right? So in terms of system memory, RAM, random access memory, where is that on this table? Well, it's sitting right across from the North Bridge on a very fast data bus, and you have 100 nanosecond access times, right? And but it's still not the fastest memory. So the thing I want you to understand is that this is volatile. Up to these first four are volatile. This is non-volatile. Everything down, everything from this point down is non-volatile. So from EEPROM on down is non-volatile, meaning it's gonna disappear. Now, we said that if you power off the computer, what's in the RAM is lost. It takes about 30 seconds for that data to disappear, and there is video of students at Princeton University taking the RAM modules out of a laptop and blasting it with upside down canisters of compressed air to freeze it. And then they can stick it in a reader and they can get the data off of it to crack somebody's password. It's pretty scary, but in any case, what I want you to understand is that RAM chips are semi-volatile, meaning you have about 30 seconds before, once the power is gone, it's lost, okay? Just remember that 80-20 rule, right? So the closer you get to the CPU, the faster it is, the smaller it is, the less distance to the CPU. Here's another diagram. So this is on chip. What they should say is on the package. So I don't like this diagram because technically it's not correct. The registers are on the chip proper. L1 is on the, well, it's in the die, but it's not necessarily in the core. And then the L2 is in the package, but it's further away than the level 1 cache. Then they have this level 3 cache. In servers, they have another kind of cache. It's a static RAM cache. And they put it on the motherboard, and it's supposed to help with data input and output in data centers. So for high performance computers, there's a level 3 cache. And you have regular memory, and then you have secondary storage or virtual memory that's hard disk based memory. So you increase in size as you get further away from the processor, and you increase in speed as you get closer to the processor. It's another way of looking at it. Increase in size, increase in speed. Does everybody understand that? Yes, no? Maybe?
May you go over it one more time, please?
Okay. So in terms of system memory, you have the random access memory that's built with logic gates that disappears when the memory is turned off. And that's everything through SDRAM or main memory. So on this table, it's this row right here. So that's electronic memory, and it disappears once the power goes off. The higher up in the table you get, the closer you are to the actual core of the CPU, the ALU of the CPU. The registers are in the CPU. The level 1 cache is on the die, but it's not in the core. So it's static RAM. It looks like it's inside the chip, but it has to do with the way that this stuff looks. So each of these dies could have multiple cores, CPU cores. Here's a great way to look at it. So you could have multiple cores on the die, and within each core is the register memory. On the die is the L1 cache. On the package is the L2 cache. Right nearby on the north bridge is L3 cache if you have a fancy schmancy system. And the further away you go, once you get to the system memory, from that point on, it's all disk memory. Basically, it's all disk memory. Does that help?
Yes.
Okay. So the farther you are from the chip, the larger the memory is, but the slower it is, because there's more distance. The closer to the chip, the smaller the memory, the faster it is. That's the thing we want you to understand. All right, so there's a lot of links on this, and you're going to be expected to spend the time to go into this. So this one in particular, it gives you some background on memory registers and the DFF flip-flops. And then here we talk about static random access, right? Then we have memory methods. Now, memory can be written, all right, so data can be written in different ways. You've all heard of the term stacks, maybe, at this point? Data structures like stacks. So when we talk about how data and instructions are written to memory, there are two basic methods to understand when data and instructions are written to memory. It's first in, first out, and first in, last out. And so here's what we mean. So first in, last out runs in RAM. First in, last out is how RAM is loaded. It's in virtual layers of data and instructions. And so the data and instructions that are used first are loaded onto the RAM, and they come off last after everything else is done. With static RAM, the method of writing data and instructions to that memory register is different. It's first in, first out. So this is on the physical layer. On the hardware layer, this is performed by software. This is performed by hardware. On static RAM, the data that's used first is also the data that comes out first. So which one do you think is going to produce data output faster? First in, last out, or first in, first out?
First in, first out.
First in, first out. Yeah. The other thing that you'll find out is that first in, first out is that method shows up again for certain types of network equipment, like high performance network switches or routers. They have SRAM, and so the network data, first in, first out, you get very, very quick turnaround on network traffic. The important thing to remember is that your active workspace on the computer, the workbench, is your SDRAM. Now I want you to see the difference here. SDRAM is the random access memory, the main memory of the system. SRAM, that's cache memory. It's very small, it's very fast, it's closer to the CPU. That is not main system memory, right? So don't get confused between SRAM and SDRAM, okay? It's very important. A couple of other things I'd like to tell you about is that sometimes the memory modules, dual inline memory modules, dual inline memory modules, that's what DIMM stands for, right? If you have a laptop, it's called a SODIMM, right? It just means short, right? It's important to click every one of these so you can see specifics about it. Video memory on video cards is dual ported for high performance. What do we mean by dual ported? When we say dual ported, we mean that there's an extra set of inputs and outputs so that you can input and output simultaneously. That's what dual ported means. So video memory, the memory that's on video cards, is dual ported. There's also this other term about synchronous, right? So we said synchronous dynamic RAM. If you have memory in banks, can everybody see this right here? If I ask you to show me where the RAM was, could somebody describe for me where the RAM is on this diagram? I mean, it's labeled, right?
It's on five wait slots.
Okay, those are the
DIMM
IO,
socket.
those are IO slots on the south bridge, right? Here's the CPU, the RAM is closest to the CPU. Whenever you see DIMM, that means dual inline memory module that has to do with RAM. That's the system memory right here, RAM, the electronic memory. I want you to understand the idea of synchronous. If you have a single module in your system, like you buy a PC or a laptop, and then there's another empty slot open, if you buy the same speed and type of memory module, the same DIMM, then when you put two of them in there, they can work in tandem together. That means that they tag team on the data and instructions. The performance is doubled. It's called synchronous RAM. So there's interleaving, this idea of tandem activity where they tag team. It's two RAM modules working together, and they sort of double the speed of access. That interleaving only happens when you use double and triple DIMMs or modules together. What am I saying? On this motherboard, we have 4 modules, so you're going to put them in doubles. So if you have a chance to increase the memory in your system and you want to upgrade it, you're better off just buying one module if you only have one module instead of buying 2 modules. Because in even numbers, if you have DIMM sockets in even numbers, you have to pair them together in order to interleave. If you have multiples of 3, like 6 slots or 9 slots, then you triple them together. Then you triple the performance, right? But you have to have 3 of them. And when you add an extra one and you break that triplet or pair, you no longer have this interleaving, okay? So when you pair them up or you triple them up, depending on the design of the motherboard, they organize the pair of them in banks, what they call banks. That's that multiples of 2 and 3 DIMMs, right? And they're interleaved, which means they work together as a team, and that way you get much better speed. So what am I saying? If you have a scenario where you have two RAM DIMMs filled, and you say to yourself, well, I'm going to improve my performance by adding more RAM to my laptop, and you only buy one, and you buy a big one. Let's say you buy a 4 gig RAM stick. You'd be better off buying 2 gig RAM sticks, because then they're interleaved. You still get 4 gigs, but they're working in tandem. So pairing them up or tripling them up is a big deal. And I want you to understand this idea of tandem or interleaved performance. Just remember that if you have multiples of 2 for module sockets, you want to pair them up. If you have multiples of 3 for module sockets, you have 6 or 9 or 12 module sockets, then you can triple them up. And you'd use DDR3 instead of DDR2. So this dual data rate 2, you'd use 2 dual data rate 2s. You'd have a pair, they'd work in tandem. If you could triple them up, you'd have 3 of those modules together, dual data rate 3, you're tripling them up, you get multiples. Is there any question about how you can synchronize RAM modules for better performance into banks? But they have to be the same size and the same speed. If they're not the same size and speed, that doesn't happen. Any questions about interleaving and RAM? We're spending an awful lot of time on RAM. And one of the things I'd like you to understand is that in order for a PC to work efficiently, it's going to load virtual instances of the entire system over and over again by itself into RAM. I think we're going to take that up tomorrow. Are there any questions about what we've covered so far? The fact that we have different types of system memory, and we have virtual memory, right? You have this virtualization. You have virtual memory that's like random access memory, except it's on disk. You have this 80-20 rule. On Friday, we're going to talk about high performance computing. We're going to talk about CPU types and graphics processors, right? And we'll finish up with the rest of our stuff. Does anyone have any questions about the concepts we've covered to this point?
No, Dr. Kentop.
Okay, I'm going to stop sharing and stop recording.